Welcome to the e-lecture session for diploma students. In today's class, we will learn about some of the terminologies involved in the principle of operation and constructional details of a transformer. First one is a transformer ratio. Consider a transformer shown in figure 3.11 indicating various voltages and currents. Let me first tell you what are the parameters available in the diagram. V1 is the input supply voltage, I1 is the primary current, E1 is the EMF induced in the primary, phi is the flux induced in the core, this is flux, and E2 is the EMF induced in the secondary, and I2 is the secondary current, V2 is the current that is the voltage across the load. Voltage ratio, we know from the EMF equations of a transformer that E1 is equal to 4.44 phi max f n1 volt. So, this expression we have already derived in the previous session, and E2 is equal to 4.44 phi max f n2 volt. Taking the ratio of these two equations, we get E2 by E1 is equal to N2 by N1, which is equal to K. This ratio of secondary induced EMF to primary induced EMF is known as voltage transformation ratio or turns ratio, denoted by K. Thus, E2 is equal to K E1, where K is equal to N2 by N1. If N2 is greater than N1, that is K is greater than 1, we get E2 greater than E1, then the transformer is called a step up transformer. If N2 is less than N1, K is less than 1, we get E2 less than E1, then the transformer is called a step down transformer. On the other hand, if N2 is equal to N1, which may not be the case, that is K is equal to 1, we get E2 is equal to E1, then the transformer is called as isolation transformer. So, this particular transformer is neither a step up transformer nor a step down transformer. This is meant only for isolation purpose and not for voltage translation purpose. We will discuss about the ideal transformer on load. Consider an ideal transformer on no load as shown in the figure 3.12. The supply voltage is V1, and as it is on no load, the secondary current I2 will be 0. So, because there is no load connected to the secondary, so this I2 will be 0. The primary draws a current I1, which is just necessary to produce flux in the core. As it is magnetizing the core, it is called the magnetizing current, which is denoted by I suffix m. As the transformer is ideal, the winding resistance is 0 and it is purely inductive in nature. The magnetizing current is denoted by I m and is very small and lags behind the voltage applied voltage V1, as the winding is inductive. This I m produces an alternating flux phi, which is in phase with I m. The flux links with both the windings, producing the induced EMFs E1 and E2 in the primary and secondary windings respectively. According to Lenz's law, the induced EMF opposes the cause producing it, which is the supply voltage V1. Hence, E1 is in antiphase with V1, but equal in magnitude. The induced EMF E2 also opposes V1, hence in antiphase with V1, but its magnitude depends on N2. If I say one phasor is in antiphase with the another phasor, the electrical degree between these two phasors will be 180, or I can say they are out of phase with each other. Thus, E1 and E2 are in phase with each other. So, the phasor diagram for the ideal transformer on no load is shown in the figure 3.13. How to draw this? I will say first let us assume phi as the reference vector. Because of this magnetic flux you have a current. So, that current I m, that is the magnetizing current, will be in phase with phi. I can draw it over here. So, this is your phi. Because of this magnetic flux which is developed in the core, you have a magnetizing current which is I m. Since it is inductive, the voltage, that is the applied voltage, will be in quadrature with this magnetizing current, or V 1 will lead the I m by 90 degrees. Whenever you draw a phasor, you have to, with this O as a center, you have to draw the phasors in the anti-clockwise direction. Say for example, if V 1 leads phi by 90, so you have to draw the phasor of V 1 like this, which means that suppose if you have a reference here, if you rotate the phasor with O as a center, then V 1 will reach the reference point A first, and then only phi or I m will reach after 90 electrical degrees. That is the meaning of a leading vector. Now, this is 90. Then we always know that the EMF induced in the primary, that is E 1, is in anti-phase with V 1. As I said earlier, suppose two phasors are said to be out of phase with each other or anti-phase with each other, whenever the electrical angle between those phasors is 180. So, V 1 is here. So, what is 180? From this V 1 you have to take 180 degrees in the anti-clockwise direction, that is in this direction, and then you should mark. So, this is 180. So, this is E 1. What is E 2? It is in phase with E 1. So, E 1 lags I m by 90 degrees, or I can say I m will lead E 1 by 90 degrees, because when you rotate the phasor with O as a center, then phi will reach A naught, that is A first, and then after 90 electrical degrees only E 1 and E 2 will reach. So, this is how you should draw the phasor diagram. It can be seen that the flux phi is the reference phasor, I m produces phi and hence is in phase with phi. V 1 leads I m by 90 degrees, as winding is purely inductive. So, the current has to lag the voltage by 90 degrees. E 1 and E 2 are in phase and both are opposing the supply voltage. The power input to the transformer is V 1 I 1 cos of angle between V 1 and I 1. So, this is the angle between the applied voltage at the primary and the input current, or I can call it as V 1 I m cos 90 degrees, that is 0, because cos 90 is 0. This is because on no load the output power is 0, and for ideal transformer there are no losses, hence the input power is also 0. Ideal no load power factor of transformer is 0 lagging. Now, we will see the transformer on no load. Actually, in a practical transformer, iron core causes hysteresis and eddy current losses, as it is subjected to alternating flux. While designing the transformer, the efforts are made to keep these losses minimum by using high grade material like silicon steel to reduce hysteresis loss. Number 2, manufacturing the core in the form of laminations or stacks of thin laminations to reduce the eddy current loss. Apart from this, there are iron losses in the practical transformer. Practically, primary winding has certain resistance, hence primary copper loss always exists. Thus, the primary current under no load condition has to supply the iron losses, that is hysteresis loss and eddy current loss, and a small amount of primary copper loss. This current is denoted as I naught. Now, the no load input current I naught has two components. One is a purely reactive component I m called magnetizing component of no load current, which is required to produce the flux. This is called as wattless component. Number 2, an active component I w or I c which supplies total losses under no load condition called power component of no load current. This is called as core loss component of I naught. As I said already, it can be resolved, this I naught no load current I naught, I can write it here. No load current of I naught can be resolved into two components. One is I mu, that is I m, the other one is I w. So, this is the magnetizing component and this is the core loss component, both are phasors vectors. So, when you add vectorially this magnetizing component and the core loss component, you will get the no load component, no load current. Here you can see here. So, this is your phi, this is the phi phasor. I m is in phase with phi because I m is formed due to the presence of the magnetic flux. Then this is your applied voltage, this V 1, and this is E 1 which is in antiphase with V 1, this is E 2, and now this is the working component, that is core loss component, which is in phase with V 1. I m is in phase with magnetic flux. Now, I am going to add these two I w and I m. How I can add? You see here how to add two phasors, right. So, this is I w, this is I m. Now, by applying parallelogram law of vectors, whenever I want to add two vectors, what should I do? I need to draw a parallel line to this I m, a parallel line for I m, and then from I m I have to draw parallel line for I w. So, both these dotted lines cut at one point. So, you join that point which is I 0. So, I naught vector is equal to I m vector plus I w vector. So, it is a vectorial addition of these two components. So, this is your phi naught. Phi naught is nothing but it is the angle between V 1 and I naught. It is the input supply voltage at the primary and this is the no load current. So, the angle between these two is phi naught. Here you can see the total no load current I naught is the vector addition of I m and I w. Transformer on load. Now, we are going to analyze what happens to the transformer components parameters when it is applied with load in the secondary. The transformer is said to be loaded when the secondary circuit of a transformer is completed through an impedance or load. The magnitude and phase of secondary current I 2 with respect to the secondary terminal voltage will depend upon the characteristics of load. That is, the current I 2 is nothing but it is a secondary current. Current I 2 will be in phase or lag behind or lead the terminal voltage V 2 respectively when the load is purely resistive or inductive, capacitive respectively. The secondary current I 2 sets up its own ampere turns N 2 I 2 and creates its own flux phi 2 opposing the main flux phi naught created by no load current I naught. The opposing secondary flux phi 2 weakens the primary flux phi naught momentarily, hence primary counter or back EMF E 1 tends to be reduced, V1 gains the upper hand over E1 momentarily and hence causes more current to flow in the primary. Let this additional primary current be known as the load component of the primary current. The additional primary magnetomotive force sets up its own flux, which is in opposition and is equal to it in magnitude. Hence, they cancel each other. From the above discussion, it can be concluded that number 1, whatever be the load conditions, the net flux passing through the core is approximately the same as at no load. Number 2, since the core flux remains constant at all loads, the core loss almost remains constant under different loading conditions. So, this is a very important point we should always keep in mind. Since the core flux remains constant at all loads, the core loss almost remains constant under different loading conditions. Irrespective of the load, the core loss always remains same. Since phi 2 is equal to phi 2 dash, N 2 I 2 is equal to N 1 I 2 dash, that is I 2 dash is equal to N 2 by N 1 into I 2, which is equal to K I 2. So, this is a voltage transformation ratio, N 2 by N 1 is equal to K. The total primary current is the vector sum of I 0 and I 2 dash. The current I 2 dash is in antiphase with I 2 and K times in magnitude. Current ratio. For an ideal transformer, there are no losses. Hence, the product of primary voltage V 1 and primary current I 1 is same as the product of secondary voltage V 2 and the secondary current I 2. So, V 1 I 1 is equal to input volt ampere and V 2 I 2 is equal to output volt ampere. For an ideal transformer, V 1 I 1 is equal to V 2 I 2, which is equal to V 2 by V 1 equal to I 1 by I 2, which is equal to K. Phasor diagram on no load. In practical transformer, due to winding resistance, no load current I 0 is no longer at 90 degrees with respect to V 1, but it lags behind V 1 by an angle phi 0, which is less than 90 degrees. Thus, cos phi 0 is called no load power factor of practical transformer. In the phasor diagram shown in the figure 3.16, it can be seen that the two components of I 0 are, one is I m, as we have discussed already, one is I m, this is the magnetizing component of the no load current, and this is I 0 is a core loss component of the no load current. So, I m is equal to I 0 sin phi 0, this is the magnetizing component lagging behind V 1 exactly by 90 electrical degrees. I w is equal to I 0 cos phi 0, this is the core loss component which is in phase with the V 1. So, the magnitude of no load current is given by the expression by applying parallelogram law of vectors. I 0 is equal to I m vector and plus I w vector, or the magnitude is given by I 0 is equal to square root of I m square plus I w square. While phi 0 is the no load primary power factor angle, the total power input on no load is denoted as W 0 and is given by W 0 is equal to V 0 I 0 cos phi 0, which is equal to V 0 I w. It may be noted that the current I 0 is very small, about 3 to 5% of the full load rated current. Hence, the primary copper loss is negligibly small, hence I c or I w is called core loss or iron loss component. Hence, power input W 0 on no load always represents the iron losses, as copper loss is negligibly small. The iron losses are denoted as P suffix I and are constant for all load conditions. So, W 0 is equal to V 0 I 0 cos phi naught, which is equal to P I, which is same as the iron loss. Then phasor diagram or vector diagram on load for different power factors. So, this is the equivalent circuit diagram. I will zoom it on, you can see here, right. So, this is the applied voltage, input applied voltage. So, this is the equivalent circuit. For simplification or and analysis and discussion purpose, we are making this equivalent circuit so simple. We are replacing the resistances and inductances in such a way that it forms a simple circuit. So, this is V 1, R 1 is the primary resistance, X 1 is the primary inductance, E 1 as I said earlier, it is the induced EMF across the primary, E 2 is the induced EMF across the secondary, R 2 is the secondary resistance, X 2 the secondary inductance, V 2 is the terminal voltage across the load. Here R 1 primary winding, resistance, everything has been explained here. I 1 is the primary current, I 2 is the secondary current. Now, I 1 is equal to I naught plus I 2 dash, where I naught is the no load current, I 2 dash is the load component of current decided by the load. So, it is the secondary current referred to the primary. So, it is the I 2 is the secondary current, whereas I 2 dash is the secondary current referred to the primary. The primary voltage V 1 has now 3 components. One is E 1, the induced EMF which opposes V 1, I 1 R 1, the drop across the resistance which is in phase with I 1, I 1 X 1, the drop across the reactance leading I 1 by 90 electrical degrees. So, V 1 is a combination of V 1 vector is a combination of minus I 1 plus I 1 R 1 plus I 1 X 1, these all these are phasor addition. So, V 1 is equal to minus E 1 plus I 1 Z 1, because I am going to combine I am going to take this I 1 out. So, I 1 is a common element here, R 1 plus j x 1 will give you Z 1, that is the impedance in the primary. The secondary induced EMF has also 3 components, V 2 the terminal voltage across the load, I 2 R 2 the drop across the resistance which is in phase with I 2, I 2 X 2 the drop across the reactance leading I 2 by 90 electrical degrees. Now, I am going to have the phasor addition of V 2 and then drop across resistance and drop across the inductance. Now, E 2 is equal to V 2 plus I 2 R 2 plus I 2 X 2, all are phasors. So, V 2 vector is equal to E 2 minus I 2 into R 2 plus j x 2. So, V 2 is equal to E 2 minus I 2 Z 2, where Z 2 is the impedance of the secondary. The phasor diagram for the transformer on load depends on the nature of the load power factor. Let us consider the various cases of the load power factor. It can be a unity power factor, it can be a lagging power factor, or it can be a leading power factor. So, all these cases we are going to have a look on. So, first one is unity power factor, that is cos phi 2 is equal to 1. As the load power factor is unity, the voltage V 2 and R 2 are in phase. Steps to draw the phasor diagram are: consider a flux phi as the reference. So, this is a phi which is the reference angle. E 1 lags phi by 90 degrees, reverse E 1 to get minus E 1. Then E 1 and E 2 are in phase, assume V 2 in a particular direction, I 2 is in phase with V 2, add I 2 R 2 and I 2 X 2 to get E 2, then reverse I 2 to get I 2 dash, because I 2 is the secondary current, I 2 dash is nothing but it is the secondary current referred to the primary. So, add I naught and I 2 dash to get the input primary current I 1. Add I 1 R 1 and minus E 1 to get V 1. The angle between V 1 and I 1 is phi 1. Similarly, cos phi 1 is the primary power factor. Remember that I 1 x 1 leads I 1 direction by 90, I 2 x 2 leads I 2 by 90 electrical degrees, as current through the inductance lags the voltage across inductance by 90 degrees. The phasor diagram is shown in the figure 3.18. Then we will consider the case 2, lagging power factor load cos phi 2. As load power factor is lagging cos phi 2, the current I 2 lags V 2 by angle phi 2. So, the only changes in drawing the phasor diagram is to draw I 2 lagging V 2 by phi 2 in step 5 discussed earlier. Accordingly, the direction of I 2 R 2, I 2 x 2, I 2 dash, I 1 R 1 and I 1 x 1 will change. Remember that whatever may be the power factor of load, I 2 x 2 leads I 2 by 90 electrical degrees and I 1 x 1 leads I 1 by 90 electrical degrees. Now, the third case is leading power factor. As the load power factor is leading, the current I 2 leads V 2 by angle phi 2. So, the change is to draw I 2 leading by an angle phi 2. All other steps remain same as before. The complete phasor diagram is shown in figure 3.20. Now, we will move on to the equivalent circuit of a transformer. The term equivalent circuit of a machine means the combination of fixed and variable resistances and reactances which exactly simulates the performance and working of the machine. For a transformer, no load primary current has two components, as we discussed earlier. It is I m and which is equal to I naught sin omega I naught sin phi naught, which is the magnetizing component. I c is equal to I naught cos phi naught, which is the active component. I m produces the flux and is assumed to flow through the reactance x naught called no load reactance, while I c is the active component representing core losses. Hence, is assumed to flow through the reactance R naught. Hence, the equivalent circuit on no load can be shown as in the figure 3.21. The circuit consisting of R naught and X naught in parallel is called exciting circuit. From the equivalent circuit, we can write R naught is equal to V 1 by I c and X naught is equal to V 1 by I m. When it is connected to the transformer, then secondary current I 2 flows when a load is connected across it. This causes a voltage drop across R 2 and X 2. Due to I 2, the primary draws an additional current I 2 dash, which is equal to I 2 by K, where K is the voltage transformation ratio. Now, I 1 is the phasor addition of I naught and I 2 dash. This I 1 causes the voltage drop across the primary resistance R 1 and reactance X 1. Hence, the equivalent circuit can be shown as in the figure 3.22. Before concluding this session on transformers, we will have a quick recap of whatever we have learnt in this session. So, we have done few problems on motors, and then we have switched on to the analysis of single phase transformer on no load, and we have learnt about the various components of no load current, that is magnetizing component and the core loss component at no load, and then we have analyzed the transformer on load also, and finally, we have derived something about that is the equivalent circuit of a transformer. Thank you.